Hey guys, this lesson is 9.6 from Calculus BC, and this is the ratio and root test. We're going to start off with the ratio test, okay? And when they're asking for the infinite sum of a sub n, that's going to be the series we're working with. What we're going to do is we're going to test if this limit, okay, which this limit is as n approaches infinity of the original series, but with 1 added to each of the n's, divided by the original series, okay? If the answer to that limit is less than 1, it converges. If it is greater than 1, it diverges. But if we get 1 as an answer, then we'll have no conclusion. So some quick reminders before we start these questions is whenever I have a term with an exponent of two things being added, we can split that with multiplication, each of them carrying the same base. And then splitting factorials, remember a factorial, you're always multiplying one less. So if this says n plus 2, I'm multiplying it by n plus 1, and then n, and then we could even go into n minus 1. Your goal is going to be to stop where it's going to be easiest to cancel out and clean here, okay? These questions aren't too bad. If you're confident with algebra, you might enjoy these here. A tip to help you know when to use the ratio test is if you spot n factorials or multiple n's throughout the question. Let's take a look. This first question here reads the infinite sum of 2 raised to n over n factorial. So the fact that I see an n in both the numerator and the denominator, I see a factorial, an exponent. I'm going to start this off by saying the limit as n approaches infinity. And since in this division, it's going to end up with a fraction over fraction, I'm going to go ahead and write that division horizontally. So the first one is the original one with 1 added to each of the n's, divided by the original. Okay. On my next step, I'm going to start to clean and I'm going to do my keep, change, flip. Remember, notation-wise, you have to write that limit until you complete it, okay? So the first split that I'm going to do is I'm going to write this 2 to the n plus 1 as 2 raised to the n times 2 raised to the first over, and then I'm going to split my factorial the way I have it here. Now, when I flip, okay, before I write this, this is going to be an n factorial over 2 raised to the n, okay? My goal is going to be to try and cancel this n factorial with something down here. So I want to take this down from n plus 1 to n, right? See it here? So I'm going to say n plus 1 times n factorial. So now hopefully you can see a lot of things you can cancel. This 2 raised to the n cancels, and this n factorial cancels, okay? So now I am writing the limit as n approaches infinity of the absolute value of 2 over n plus 1. Okay? Now, when I plug this in, this would give me 2 over infinity plus 1. It's already positive, so I don't need the absolute values, which you can count this as 2 over infinity, which is bottom heavy, so it equals 0. And because 0 is less than 1, then we can say that this converges. And you are done with that one. Let's take a look at this next one. A little more complicated, more n's involved. We're going to start off with the limit as n approaches infinity of the absolute value. Now, if this is an n squared, I'm going to call this an n plus 1 squared times 2 to the n plus 2. So if this was n plus 1 and I'm adding 1, now I have n plus 2. All right. Over 3 raised to n plus 1. And now I'm dividing. If you get quick at these, you can go straight to multiplication and flip it. I'm just going to, for the sake of the work, show each step. Okay, now I'm just going to flip this one and start to clean some things. All right, so here I'm going to leave this n plus 1 squared. There's not much I can do with that. This is going to be a 2 to the n times 2 to the second. And this will be a 3 to the n times 3 to the first. I'm going to flip this, and this is going to be a 3 raised to n over n squared. And I'm going to change this to a 2 raised to the n times 2 raised to the first. Okay. Now let's go see if there's anything we can cancel out. I've got these 3 raised to n's. I have the 2 raised to n's. Okay. Oh, I'm sorry. I just noticed I put 2 raised to the n here. That should be 2 raised to the 2, okay? So I went ahead and paused the video and fixed that for you there. So what I do have left, I have this n plus 1 squared, a 2 squared, and then I have a 3 to the first and a 2 to the first. Notice I can still clean here. That exponent of 2 means that there's 2 of them here and there's 1 of them here. So I can cancel out this 1 with 1 of the ones up here, and I'm just left with 1 of them, okay? So if I rewrite this, I have the limit as n approaches infinity of n plus 1 squared times a 2 over 3 and then this n squared. Okay, you may prefer to write this as that 2 in the coefficient. And then when I solve this limit, remember when I plug in infinities, if the exponents, the highest exponent is the same, it serves as the horizontal asymptote rule. So the answer to this limit is just the coefficients, which is 2 over 3. And because that is less than 1, this also converges. When I look at this next example, I've got so many n's here. I've got an n raised to the n in the numerator and then an n factorial in the denominator. That's what leads me to do the ratio test, okay? So I'm going to start off with the limit as n approaches infinity of the absolute value of this n needs a plus 1. And so does the 1 in the exponent, okay? And then divided by the original. I'm moving on to my next step. I'm going to multiply by the reciprocal, my keep, change, flip, and I'm going to start cleaning here. So remember, each of these get that exponent. So I'm going to say n plus 1 raised to the n times n plus 1 to the first. Okay, and remember when I do my keep, change, flip, I'm going to have this n factorial on the top and this n raised to n down here. So this denominator, I want to clean until I can get an n factorial. So I have n plus 1 times n factorial. Okay, let's see if there's anything we can go cleaning. I see this n factorial. I also have this n plus 1 that cancels out. So let's go looking at what we have left here. All right, so the entire numerator and the entire denominator have that n in the exponent. So I'm going to take a minute and rewrite this, because if I plug in my infinities, I'm going to get infinity over infinity, which is an indeterminate, okay? Right? So with indeterminates, I could either do derivatives or I can keep trying to clean. Here, the derivatives are pretty complicated. So that's why I'm going to start to clean this, and I'm going to say n plus 1 over n, and the whole thing has an exponent of n. All right, if I plug infinity here, I'm still going to get infinity over infinity raised to infinity. That is still an indeterminate. So I do notice that if I split this, I have n over n plus 1 over n. And hopefully this is starting to look familiar to you. Okay. We have, actually, I'll come down here. The limit as n approaches infinity. Earlier on in this year, we've repeated it a few times. We have seen something that looks like this pop up as a limit that you were supposed to memorize in BC. And that is that special third limit, which equals e. Okay? And now because e, which is a decimal of 2 point and then some, this is definitely greater than 1, which means that this diverges. Okay? Let's go ahead and look at our next one. Okay? I see multiple n's here, so I know I'm trying my ratio test. Now, because this rule starts off with you putting on absolute values on the outside, you can ignore this from the beginning, okay? Because if that is alternating signs and I have an absolute value bar, we don't care about our signs. So I'm going to have the square root of n plus 1 over n plus 2 divided by square root of n over n plus 1. Okay, I'm going to work on my keep change flip here. All right, and there is not much cleaning that I can do here. So at this point, if I try and put my infinity in, I can use my horizontal asymptote rule, which says I'm going to analyze the highest exponent. Now notice I have not multiplied this, so if I want to analyze the highest exponent, I need to see what it would be if I did multiply it. So look at the highest here and the highest here. This would be n to the 1/2 and n to the first. And in the denominator will also be n to the 1/2 times n to the first, meaning that my highest exponent is going to be the same in the numerator and in the denominator. So by horizontal asymptote rule, I can look at what the coefficient would be. Well, if my coefficient is 1 and 1 and 1 and 1, it means when I multiply all those ones, I'm just going to get 1 over 1, which is 1. And I know that when the answer of this is 1, I have no conclusion. Now remember, anytime you get no conclusion, you are not stuck here. You just need to try another test. Now, because from the beginning this had the alternating symbol, I can try the alternating rule, right? So step 1 was to check if it alternates. Well, it definitely does, right? I had crossed that out just for the sake of the ratio test, all right? But if I'm looking back at it again, I do take it into account. 2, I want to look at the limit as n approaches infinity of a sub n, which a sub n is what's left over when I'm not paying attention to that alternating. So the limit as n approaches infinity of square root of n over n plus 1. Okay, now I want to make sure and prove that this equals 0. So if I'm doing a limit as n approaches infinity, this is our horizontal asymptote rule. My exponent in the top is raised to a 1/2, and the bottom is to the first, which means this is bottom heavy. Bottom heavy means that it equals 0. That's what I was looking for. My third is to confirm that it is decreasing. Okay, now I want to talk about doing this the quick version, okay? If I start plugging bigger and bigger numbers in, try a quick number like something big, like 20 or 25. And I'm going to say 25 because there's a square root here. So if I were to plug in 25, here square root of 25 is 5, and here to get 25 plus 1, which is 26. 5 over 26. Notice that my denominator, the bigger number I put, is going to keep adding 1, and this is going to be doing a square root, which makes it smaller, which means that my denominator is getting bigger, and my numerator is going to keep getting smaller, which means my number as a whole is getting smaller. So it is decreasing. Okay? So by the alternating rule, the fact that we're able to prove these three, we know that this converges. Next, we're going to look at our root test, okay? So this test is used when we have an n that is on the exponent in the numerator and the denominator, okay? So given that we have this series, okay, if you spot, so for example, look at this one here. You see how there's an n in numerator and denominator? That's our key way to catch it. We're going to do the nth root of the absolute value of the inside, and we're going to do the limit to infinity of that, okay? I know this sounds complicated, but when you see these examples, this is one of the easiest rules, okay? If the answer to that limit is less than 1, it converges. Greater than 1 diverges, equals 1, no conclusion, okay? So if I look at this first one, the fact that I have this n in the numerator and 1 in the denominator, it means I can do the limit as n approaches infinity of the nth root of the absolute value of the original question. Okay? Now remember, if the exponent and the root are the same, you can cancel them out, okay? If you would like to rewrite it this way so that it's easier to see, you can say e raised to 2 over n, and then all of that raised to the n, because remember, I'm allowed to give exponents to numerators and denominators. As long as what I'm separated by is multiplication and division, it's allowed. Okay, so here, this nth root and this n cancels, and what I'm working with is the limit as n approaches infinity of the absolute value of e squared over n. Okay, now if I plug that infinity in, this is e squared over infinity. Don't need the absolute value bars because this is already positive, and this is a bottom heavy fraction, so this equals 0. And because 0 is less than 1, then this converges. Okay? Let's take a look at the next one. Now, the fact that this one was already written with this n in the exponent, remember, when you see it written like this belongs to the numerator and the denominator. I can go straight to my root test. Okay, that nth root and that n exponent are going to cancel, and that 3 belongs to both the numerator and the denominator. So let's rewrite it. Now you can leave the absolute value there for now, or you can already take into account what that cubed and that that negative is going to do. I like to leave it to the end. Okay, now my limits to infinity, if my exponent is the same, which I know if I clean this, my highest exponent would be a cubed. I have cubed on the top and cubed on the bottom, which means my answer to this would be an absolute value of negative 3 over 2. The absolute value takes away the negative, and I have 3 over 2. And that 3 over 2, I'm sorry, let's rewind a little bit. I almost forgot about this cubed here, okay? We can't forget about how that cubed would affect it. This gives me 27 over 8, which is greater than 1, Therefore, this diverges. This last question for the root test, I can clearly see that n up here in the exponent. So I'm going to do the limit as n approaches infinity of the nth root of the absolute value of ln of n over n. All of this here, sorry, was raised to the nth power, okay? So those n's are going to cancel. And now I'm working with the limit as n approaches infinity, absolute value of ln of n over n, okay? If I plug this infinity in, ln of infinity is infinity. This is clearly an indeterminate, so I'm going to have to use L'Hopital's. Okay, the derivative of ln of n is 1 over n, and then divided by derivative of n is just 1. Okay, anything divided by 1 is itself. I know when I plug this in, I'm going to get 1 over infinity, which is bottom heavy, so it equals 0. And because that is less than 1, we know that this converges. All right, guys.